Thank you everybody at CQT for inviting me and organizing my visit here. And so the talk I'll give today is about randomness. And roughly the sketch of what I'll talk about is first, what is randomness in general? Some general considerations about this. Then a quantum phenomena we call non-locality, and this phenomena, how it connects to randomness in quantum theory. And then I'll go to applications, how this phenomena can be used to certify that we have good randomness sources, can be used to certify that we've got good cryptographic systems, can even be used to certify that we have quantum computers that work well. And before continuing, let me just mention that people in CQT have been working a lot on these topics, and some of the most important contributions are in fact due to Arthur Eckert, the head of CQT, and Valerio Scahani, who's probably someplace in the audience over there. And well, certainly they'll recognize their contributions when I mention them or talk about the topics. So randomness, well, let's start very far back, step back, and look at the connection even with philosophy. And in the 18th or 19th century, physicists had discovered how, well, Newton's laws, classical mechanics, and Laplace maybe most famously realized that Newton's laws were completely deterministic, in the sense that if you knew, say, the positions of all the planets around the sun at some time and their velocities, you could compute everything, all their positions in the future, and you could compute all their positions in the past. And he extended this and said, well, this is maybe true for all of nature. And so all nature should be deterministic. And deterministic means if we know the situation now, then we can predict all of the future and we can predict all of the past. At least in principle, if we had enough, or now we would say enough computing power. And this is an extract, but in French, unfortunately, of Laplace's text in which he explains this. And if we go, so this is determinism. And from the philosophical point of view, you can contrast it with free will, which is much more difficult to define precisely, but more or less means that it's the possibility to make choices free from external constraints. And these words are all a bit vague, but I think it's difficult to make them more precise. And then you can connect to other things, for instance, to more social considerations. For instance, Nehru, the founder of the Indian state, said that life is like a game of cards. The hand you are dealt with is determinism. The way you play it is free will. So this is more social determinism. And so randomness sort of certainly is important in understanding what is our position and how we understand our position in life. It's also it appears very often, say, in art. For instance, in paintings, this is a painting by Jackson Pollock, and clearly he used a lot of randomness to make this painting, which I at least find quite appealing. And it also appears, say, in cinema. For instance, these are two films by Alain Resnais, a famous French film director, and they're based on plays by Alan Ayckbourn, who's a famous English playwright. And in these films, the stories start exactly the same in the play also, and then at some point somebody smokes a cigarette or doesn't smoke a cigarette. And that changes the future of the story. And people will divorce or get married or have children depending on whether this cigarette was smoked or not. And then there are other branching points. And I think in the play, there's something like 40 different endings, depending on different incidents, which each have an amplify their consequences. And, well, Resnais and Ayckbourn were playing on this idea that small events can have tremendously big consequences. And this, well, we also know in physics, we call it the butterfly effect. And the picture here was the idea that if you have a butterfly that flutters its wings or doesn't flutter its wings someplace in the Amazon forest, the little air currents it creates could get amplified and maybe sometime later determine whether there's a tornado someplace completely different or no tornado. But this is not randomness. This is the amplification of a small effect into big consequences. And so it's completely compatible with Laplace's determinism. If you knew the butterfly movement and you knew all the configurations of the air and everything about the atmosphere at that time, well, you could integrate the equations of meteorology and determine whether or not there would be the tornado. So it's, in principle, completely deterministic, but it may be very complicated to determine the consequences. Randomness is also important, for instance, in game theory. If you play poker or have learned a little bit about poker, well, in poker you should adopt a random strategy. People bluff in poker, but you shouldn't bluff in a systematic way. You shouldn't bluff, you should bluff sometimes, but it must be at random times. Otherwise, your adversaries will use this to take all your money. So in games, when you're playing against an adversary, it can be very useful to adopt a random strategy, and then your adversary, well, he doesn't know what is the best way to counter it. It's very interesting that biology has used sometimes random strategies like this. So this has probably been strategies which have evolved through natural selection, and nature has found that the best way to play the game of survival of the fittest is to use a random strategy. Here are two examples. The first is meiosis, which is the process in which you make the sexual cells, ova or spermatozoids. And so this is a parent cell which contains, in this simple picture, 2 chromosomes, one from the mother, say in white, and one from the father in red. And then there's a complicated process in which you make the sexual cells, and these contain only 1 chromosome, but they contain random parts of the initial father and mother genome. So when your children, who will get part of their chromosomes from this cell, say, they get random parts of your parents' chromosomes. And this random choice has been selected by evolution as probably a good way of trying to produce evolutionary fit offspring. Another example is the immune system, which is the whole system we have in our bodies to fight against foreign invaders, bacteria, viruses, and so on. And one of the main parts of the immune system is based on some special molecules called immunoglobulin, who have a central part which is fixed, and then some side parts that have a random structure. And these are continually produced in new configurations by the body, and then they're tested to see if they bind to your own body, in which they're very bad because they would give autoimmune responses. But if they don't, then they're sent out into your body to try to recognize foreign molecules. And again, the body is using a random strategy to try to find foreign molecules. I guess the idea, or the reason is that if it uses a deterministic strategy, then something which gets around this will just destroy all the population. Whereas here, you will always have, you can hope to have some people, some of these molecules which will recognize all of the possible invaders. Randomness is also very important in engineering, and one of the main topics is called Monte Carlo simulations, which is the case when you have problems which are so complicated that you can't solve them in any deterministic way, and the best you should do is to use some random approach to calculating what is going to happen. So for instance, this would maybe be the evolution of, say, some stock. I guess it's going pretty fast up. And these are random scenarios based on random external events, and you've got random evolutions of this stock. To give you an example of an application in a concrete physical problem, these huge detectors which are used at CERN to detect to make collisions of elementary particles, well, these detectors are very big, and they're so complicated nobody knows like that how they work. And to get an understanding of how they work, people run Monte Carlo simulations, random simulations of how one collision will create a whole cascade of particles, and this cascade, well, you redo the simulation many, many times, you get different cascades, and this gives you statistics on how the detector behaves. And it's these statistics which are used to compare with the experiments. Randomness is very important in cryptography. All the security of interacting on the internet, of banking, is based on randomness. Your PIN code, for instance, should be random. If it wasn't random, for instance, if it's your birthday, well, it would make somebody who stole your bank card have a very easy time to access your bank account. So it should be random, and random here is very clear what it means. It means that the adversary, the person who steals your card, shouldn't be able to guess it. It also means that, for instance, your wife's card should have a different PIN code from your own. So if somebody knows your PIN card, they shouldn't know your wife's PIN card. So randomness is clearly important in cryptography, and in fact, all of cryptography relies on randomness. You can't bake a cryptographic system without using randomness, because you must make your system in such a way that an adversary who wants to read a message, who wants to access your bank account, well, he can't guess what is the way to do it. And so the numbers used in cryptography must be unpredictable to an adversary, and even if he knows some of the random numbers, he should not be able to guess the others. And because cryptography is a very mathematical topic, this is in fact probably the place where the nature and quality of the random numbers you use is the most important. So if you go back to Monte Carlo simulations, for instance, maybe imperfect random number generator could give very good results. Here, if there's too much imperfection, well, the system is compromised. To give you a famous example how use of a bad source of randomness makes cryptanalysis easy, you can go back to the Enigma machine, which was used by the Germans during the Second World War. And so it was a hardware machine which was used to crypt the highest level messages used by the Germans. And there was a whole set of settings, plugs here, rotors, which were set. And then you typed your message and you got out the crypted message. And the Allies were famously able to crack this Enigma machine, but in fact it was because the Germans, if the Germans had used the machine to its full capability, using as much randomness as possible to choose the settings, it would have been much more difficult for the Allies to crack it. It's because they were a bit lazy that they weren't using changing as much as possible the different settings in the machine, which made it easier for the Allies to crack it. So maybe had a huge historic importance that the Germans weren't using enough randomness in the Enigma machine. So this brings us to how to generate random numbers. And another question is how to certify, to guarantee that the numbers are truly random, that is, unpredictable. And this is really difficult. For instance, this little cartoon of Dilbert, you've got this troll presenting here we have our random number generator. 99999 goes the random number generator. Are you sure that's random? That's the problem with randomness. You can never be sure. And it's really true. I mean, here, it could be that this is just the beginning of a sequence, which is a random sequence, and the troll, just by random fluctuation, the first 6 digits are 9. And it could also be that there's a defect in this animal, and it only produces 9 as output, and it hasn't yet been detected that it has a flaw. So, in fact, certifying that you've got a system which generates random numbers is really difficult. And I would say until recently, there wasn't any really good way of doing this. So the present-day solutions used to generate random numbers fall in two classes. One are digital pseudo-random number generators, which you can think of as digital implementations of the butterfly effect. You take a small random seed, a small random sequence, and you put it into an algorithm which amplifies this into a much longer sequence which looks random. But so you need this initial randomness, and then this algorithm which produces a long sequence which looks random, but in fact it's determined by the small initial seed. And you can also use hardware random number generators, that is devices which through a physical process generate random numbers. And one class you can think of as analog implementations of the butterfly effect. So physical devices which implement this kind of amplification of a small random seed into a longer sequence which looks random. Or you can use quantum randomness. And so this is the next topic of my talk is how we can use quantum mechanics to generate randomness and why quantum mechanics is indeed random. Now, to understand this, we go back to the history of quantum mechanics, which started more than 100 years ago with Planck studying the black body radiation, and then Einstein and Bohr, who set the foundations of the theory. And then in 1925, Heisenberg and Schrödinger gave a mathematical theory which could be used to predict plenty of things, the spectrum of the hydrogen atom, and well, has become one of the most successful theories in science. But the initial formulations didn't really say how to interpret what came out of this theory. And a year later, in 1926, Born gave, in a famous paper, gave what is called the Born interpretation of quantum mechanics, connecting it with randomness. Now, Born, in this paper, what he did is he realized that the quantum theory which Schrödinger and Heisenberg had developed could be applied to collision problems. So he knew that there were experiments in which people sent electrons onto atoms, and the electrons got scattered. And if you send an electron, it gets scattered, you can detect in what directions it's scattered. And you find all possible directions. And the quantum theory could be applied to this problem. So he applied it, and he found that the solution described the electron coming in, and then the electron coming out in all possible directions simultaneously. And that struck him because he knew that in experiments the electron comes in and then you're going to detect it coming out at a certain angle. So the theory wasn't describing an individual outcome, it was describing all the outcomes of the experiment at the same time. And he concluded that there's only one possible interpretation, is that phi, the mathematical object given by the quantum theory, must give the probability for the electron arriving from the z direction to be scattered in a given direction given by the angles alpha, beta, gamma. If the theory is describing all possible outcomes simultaneously, it can only be giving the probabilities of these outcomes. And then he turns to the more philosophical question, and he concludes his paper with the question, well, here the whole problem of determinism comes up. Ought there be some inner property of the atom which conditions a definite outcome for the collision? Myself, I am inclined to give up determinism in the world of atoms, but that is a philosophical question for which physical arguments alone are not decisive. So what Born was thinking here is that it could be that, for instance, the electron or the atom, say here, the electron has a little label in it, some additional information, which we now call hidden variables, which tells the electron, this time when you collide with the atom, you scatter at 30 degrees. Maybe there's also some information in the atom. When these informations get together, they determine in what direction is scattered the electron. So you can explain the experiment by some completely deterministic model, where you have this additional information, but this information isn't contained in the quantum theory. And okay, Born at this point, he thought this was just a philosophical question, whether or not you could decide whether quantum theory was really random or whether there was these hidden variables in it. And now, as I'll explain, we know the answer to this question. Now, this paper of Born gave rise to a reaction immediately by Einstein, who in a letter to Max Born, well, he argued that this didn't make sense, nature could not be random, and he famously said, God does not play dice. So, Born's Gedanken experiment, today you can buy it. You can buy random number generators, which, for instance, work like this. You've got a photon source, it sends a photon, a beam splitter, and with 50% chance the photon goes straight, with 50% chance it's reflected in this direction, and which detector clicks tells you what, gives you a random bit. And you can buy this. These are examples of some commercial devices with the optics here is very simple. It fits in a little piece of this box, and the rest is mainly electronics to count the photons and connect to a computer. So can we do better? Can we understand whether quantum processes are really random? And can we certify that the outcomes of these random number generators are really random? And to make progress on this, we have to turn towards non-locality and entanglement. And the starting point for this reasoning is an experiment, a Gedanken experiment, a thought experiment, which was proposed by Einstein, Podolsky, and Rosen in 1935, so 10 years after Born's paper, in which they imagined a situation where you have a source which produces a quantum state of two particles. And this state has the property that Alice, she's got a measuring device, Bob has a measuring device, and these devices will always light up. They have two lights, a red and a green light, and either both lights will light up green or both lights will light up red. And this is always what happens. And quantum mechanically, we would describe this in this way with a state which contains both outcomes at the same time. Quantum mechanics describes all the outcomes simultaneously, but if you observe just green, green, or red, red. And you can explain this by a hidden variable model, a model which is deterministic, if you suppose that the particles, when they're emitted by the source, have a little label which tells this time we should turn on the green light. And if the particles have the same label, then they'll both turn on the green lights or they'll both turn on the red lights, and the system will obey exactly these statistics. But Einstein EPR found this weird because the quantum state is describing both outcomes at the same time. And the next step in this reasoning was taken 30 years later by John Bell. What's happened? Sorry, I don't know why this occurred. Who imagined a new experiment. I'm sorry, the left side is cut here. With the two experimentators, Alice and Bob, and they have two detectors which now have a lever. So you can choose what the measurement device is going to measure, with a lever in the up position or in the down position. Here, Alice's lever is up, Bob's is down. And he imagined the situation where, according to the choice of measurements, you want the following results. If at least one of the levers is up, for instance, in this case, you want, the picture is actually not going the right way, but you would like both lights to light up the same. So you would write green, green, or red, red. And if both levers are down, you want opposite colors on the measuring devices. And this situation, where you can also try to explain it, to realize it with a hidden variable model, a model which is completely deterministic, in which Alice's particle has some instructions which tell her how to behave when she reaches the detector. Now the instructions must be more complicated. They must say, well, if the lever is in the up position, you must light up the green light. If it's in the down position, you must light up the red light. Same thing for Bob's lever, Bob's hidden instructions. And these instructions should be such that they reproduce these correlations. Now, if you try to do this, you find out that it doesn't work perfectly. The best you can do is reproduce these correlations 3/4 of the time. For instance, suppose that Alice's particle always is going to light up the green light, and Bob is always going to light up the green light. Then whenever one of the levers is up, you've got green, green, fine. But then when both levers are down, you're going to have green, green, which is not correct. So it's very easy mathematical exercise to show that these models can only reproduce the correlations Bell wanted 3/4 of the time. If you turn to quantum theory, you produce some quantum state of two particles. You send one particle to Alice, the other to Bob. In this case, you get 85% of the time correct, so more than 3/4. This is a very surprising prediction of quantum theory because it's not compatible with these hidden variable models, these deterministic models. And so this prediction of quantum theory has now been tested experimentally in many, many experiments. This is maybe the first and most famous of these experiments by Alain Aspect in 1982, in which he had a source which produced pairs of photons, nu1 and nu2 here. And these photons, this device here corresponds to the lever position. So in one case, this sends the photon to one kind of measuring device, and if this detector clicks, it corresponds, say, to a green light coming on. Or it can send the photon to this measuring device, and if this clicks, it turns out to be, say, again, the green light. And if the detectors don't click, it's the red light which comes on. So you can run this experiment, and so this is like the switch in Alice and Bob's experiment. These are the different ways the measuring devices work. These are the measurement results. And this experiment produces exactly the correlations expected by quantum theory. There have been other experiments. Recently, there have been experiments over like a kilometer with basically instantaneous measurements on Alice's and Bob's side. This one was done in Holland a few months ago. There have been optical experiments which also work very well now. And the main difference between these experiments and, well, the first is that the measurements were basically instantaneous compared to the previous one, and that the detectors always detect when the events always respond. In this experiment of Alain Aspect, a lot of the photons were in fact lost. So the experiments have improved, but basically they're always saying the same thing. Quantum mechanics works, and it always gives this 85%, or at least above the 3/4, which you have from the classical simple theory. So how does this connect to randomness? There's a long history of works on this, some of which, there's a long history of works on the connection between non-locality and randomness. And you can try to understand the connection in the following way, is that if we look at these correlations, which we want to reproduce, so if one of the levers is up, we want the same color. If both levers are down, we want opposite colors. And let's select one possible subset. So for instance, here, we select all green or green-red in that case. Now this is very good. It would work perfectly. It would give 100% times the correct result. The problem is that if this is the case, Alice and Bob can communicate instantaneously. The way it works is that, you see, Bob's light here will only light up if his lever is in the down position. So he puts his lever in the down position, and then it'll light up if Alice put hers in the down position, but if she put her lever in the up position, he will get a green light. So Bob puts his lever in the down position, and then Alice, just when the particle arrives here, she switches her lever, and this determines what is going to happen, the color which is going to light up on Bob's side. So it works perfectly, but it allows Alice to instantaneously communicate to Bob. And you can easily check in the experiments whether this is the case by analyzing the data, and one sees that this is not the case. Alice and Bob, you would have instantaneous communication. You can easily test it in experiments and see that the data doesn't allow this instantaneous communication. And the conclusion is quite easy to reach. It's, again, a simple mathematical result, is that if the correlations between are correct here more than 3/4 of the time, so you can't explain them with these local models, and if they do not allow instantaneous communication between Alice and Bob, then the results must be random. You cannot explain them otherwise. So they must be random. They must be undetermined until the moment when you do the measurement. And so this gives us a new kind of randomness generator, in which this is my next slide. Yeah. In which we know that the results here, the lights lighting up, are random, given that the correlations obey this more than 3/4 of the time. So we've got a certification based on what's happening in the experiment that guarantees that what's coming out is random. And so what have we learned from all this exercise and all these experiments? Well, first, we've learned that nature is random, and we've answered Born's question. He was saying, well, there's no way to decide whether nature is random or deterministic. It's a question of philosophy, but in fact, you don't have the choice. These experiments with two particles can only be explained if you suppose that nature is random. And we only obtained this conclusion by looking at the statistics of the measurements, at the correlations between what Alice and Bob did with their levers and what came out as what lights lit up. And we don't need any hypothesis on the inner workings of the devices, whether it was photons which were coming, how they were measured, it could be electrons. All this becomes irrelevant. We only use the statistics to reach this conclusion. There's some requirements you need to have, which are like hypothesis behind these theorems, but they're very natural. You need some initial randomness to choose the positions of these levers, and you need to isolate the devices. They mustn't be able to communicate with each other. And so these new features, well, what we would like to do is to try to turn this into useful features which we can use for applications. This is a bit the whole philosophy of quantum information, is to turn the weird aspects of quantum theory into useful features which we can use in applications. And so can we use this in applications? And one application is to expand a random seed. Certified randomness expansion, or we also call it device-independent randomness expansion. So the idea is that we use some initial randomness to choose the measured positions of the levers, and we get new randomness coming from which lights light up. And if the correlations, the correct correlations are satisfied more than 3/4 of the time, then we know we're getting new randomness out of this experiment. And we don't need any hypothesis on what is happening inside the devices, how they operate. Of course, it could be that we don't satisfy the correlations 3/4 of the time, and in that case, well, something is going wrong, and we throw it away and try to build an experiment which works better. It could be, for instance, the experiment works well for some time, and then there's something, a component which ages, and it starts to break down. We will detect the breaking down because the correlations won't be satisfying the correct, what we expect. They won't be, again, doing correctly 3/4 of the time. And you can, by doing this cleverly, you can in fact take a small initial random seed and make a much longer, a new set of randomness. And working on this problem and trying to improve it, it was later shown that you could basically indefinitely expand your randomness. So you do it first time, you get new randomness, you use this new randomness to choose the settings for new devices, and you generate even more new randomness, and you iterate this, and you can iterate it indefinitely and generate arbitrary amounts of random numbers from a small initial seed, maybe a million bits, something like that, and then you can generate as much randomness as you want. This kind of experiment was done maybe the first time that it was non-locality experiments were applied to randomness generation was done about 5 years ago in the laboratory of Chris Monroe. In this experiment, he untangled 2 ytterbium ions. So these were the 2 systems on which Alice and Bob carry out their measurements. They're in some traps here. And then these ions were measured. The experiment was very slow. Sort of the statistics suggested there were something like 40 new random bits generated after 1 month of operation. So nothing you would like to really use in practice. But this was the first experiment. Today people can go orders and orders of magnitude faster. And this will still improve significantly over the next years. Another application is quantum cryptography. And again, we can certify quantum cryptography by non-locality. And here, well, I mentioned the contributions of Arthur and Valerio. They wrote some of the basic papers on this topic. And I won't go into the details of how you do quantum cryptography, how you can use quantum mechanics to crypt messages. But the basic idea of cryptography is that if Alice and Bob want to exchange a secret message, they need some randomness, some random numbers, and in essentially all cryptographic schemes, these random numbers must be shared. They must be the same random numbers on Alice and Bob's side, but these random numbers should not be known to the adversary. And if you have this shared secret randomness, then you can crypt messages. So Alice and Bob, you need to find a way to share between Alice and Bob these random numbers. And if you do, well then the eavesdropper, she can maybe read the message which is being sent, but she can't decrypt it. So I won't go into how you do this in practice. This kind of system, what you're going to do in using quantum theory is to use quantum communications, sending quantum states of light, to establish these shared random numbers. And these kind of schemes you can also buy today. So this is a picture of a commercial quantum cryptography scheme system, opened up, so there's some optical components, and then a lot of electronics to get the system to work, and the whole thing fits into some reasonably sized boxes. And then this is Alice's system, this is Bob's system, and they're connected by optical fiber, which allows you to send photons from Alice to Bob. And here there may be a few meters of fiber, but you can put tens of kilometers and it still works. So these systems work, you can buy them. But, once people started making these systems, people started to think, maybe are there any imperfections in the devices, in these cryptography schemes? And there were, a few years ago, a series of famous papers on quantum hacking, people who hacked these quantum cryptography schemes. Basically, they find some weaknesses. The systems weren't implemented in an ideal way, and these could be exploited to have an eavesdropper learn what were these shared secret bits which Alice and Bob think were secret. In practice, once you show how you can crack a system, then the manufacturer, well, he implements some controls in his device, in his box, so that this hacking attack no longer works. But as there have been a series of such attacks which are found, you can never be sure that a quantum cryptography system will really work correctly, that there's not some loophole in it, or it could be maybe even also, again, the devices could age, and as they age, they work less well, and then they become susceptible to attack. And so we can again use non-locality to try to solve this problem. By, again, we're going to have Alice and Bob share their have two measuring devices with two levers, two lights which can light up. They have a source here which produces correlated particles, which are sent to Alice and Bob, and they use some randomness to choose the positions of the levers. And Eve can control the source. She could even possibly have designed part of how the devices work. What Alice and Bob are going to check is whether they have the correct correlations. That is, if according to the positions of their levers, up or down, they get either the same results or opposite results only in the down-down case. And so if they get this more than 3/4 of the time, they know that they're using a quantum system and that they're using quantum measurement devices. And you can see that this allows them to produce shared randomness, because they're going to get, for instance, in the up-up position, they're going to get either green-green or red-red. So if they select the cases where they had put both levers in the up position, they know that they'll have the same results, green-green or red-red. And they know that these results are random, as I explained before. Random means that they're unpredictable to the eavesdropper, they're undetermined until the point of measurement, and therefore they're not only random, but they're secret. The eavesdropper, potential eavesdropper, cannot know what is the result of the measurement. And so we get, well, you have to work. I mean, this is a sketch of how the system works, but you can basically get shared secret randomness, which is certified, guaranteed to be secret and random by the correlations which are satisfied here. And this, again, is independent of the implementations, independent of whatever goes on in the devices. Finally, you can use non-locality, you can use these kind of experiments to certify that quantum computations work correctly. At least in principle, this can be done. And this is a non-trivial problem. For instance, very recently, there's a Canadian company called D-Wave that manufactured and then sold a number of devices in very nice boxes. Here you've got a photograph of the box. And they claim that this is a quantum computer. This is a picture of what should be inside the box, a very nice chip with a lot of electrical connections. And, well, this made the headline, the front page of Time magazine. So the question is, well, is this device really a quantum computer? Is it doing a quantum computation? Or is it maybe a fake? And, well, there have been a lot of work trying to investigate this. And people have, well, this is just one paper where people have studied this device from the exterior, trying to probe how it works and trying to understand whether there was some kind of quantum speed-up in this D-Wave machine. And the conclusion today is that most likely, almost certainly, this device doesn't exhibit a convincing quantum speed-up. But this was a very difficult conclusion to reach, and is not, certainly not, based on a certain number of tests, but you could, in principle, do better by using non-locality. By using entangled particles, you could devise a quantum computer in such a way that you just look at the statistics of what comes out of your measurements on these particles, and you're guaranteed that the computer worked correctly. So this, I'll sketch a proposal by, these authors of a few years ago. And they said that, well, among its applications of their proposal, our scheme makes it possible to test whether a claimed quantum computer is truly quantum. And the idea, well, I'm not going to explain to you how a quantum computer works. Classical computers are already very complicated. Quantum computers are even more complicated. And this way of building a quantum computer is even more complicated. So I certainly don't have the time to do this, but just in a few words, the idea, this illustration taken from their paper is going to show how to build this small quantum circuit. So a very small computation. And to do this, you're going to use a very large number of entangled particles on which you're going to do these non-local measurements. And then you do them in a series of steps. First, you do measurements which tell you that you indeed have entangled particles and that you're doing the kind of measurements you expect to do. And then you do measurements which you do first some operations on some of the particles, and then you do the measurements. Then you do operations on other particles, and you do the measurements. And finally, you run a whole complicated process on many of these particles, and you get some statistics out of all these tests. And these statistics, if they obey some correlation sufficiently, exactly as I explained before, will certify to you that you've actually implemented this computation. So in principle, it's possible to run a quantum computer in such a way that you don't need to know how it works. You don't need to trust in any way the vendor. You can just run the computation in this distributed way and learn that the computer did the computation in a quantum way. So to conclude, well, nature is random, and basically today we've proven this experimentally using quantum non-locality. And this quantum non-locality, the experiments on pairs of entangled particles, can be used for applications. They can be used to expand a random seed indefinitely. They can be used to certify that a quantum cryptography scheme works independently of how it's built. They can be used to certify that a quantum computer works correctly. And if you think of I think this randomness expansion, well, the first proof of principle experiments work today. They're getting to be pretty fast. And my expectation is, say, that within 5 to 10 years, this will become, say, semi-commercial in the sense that maybe a security agency will implement this as a new random source to add to their arsenal. Randomness is so essential for them that if they can have a better source of randomness, why not build it? Or you could have somebody implement this and make public the results and say, now we've got some random numbers in this database. You can use it for applications, not cryptography, but other applications. And the way they're generated guarantees that these numbers are random. There's no extra hypothesis. They're guaranteed to be random. Quantum cryptography requires that we do these experiments, but over long distances. And there's a sort of technological or scientific race between different groups to try to implement this. And it'll maybe take 5, 10 years to have maybe the first proof of principle experiments. Whether or not this will any time have real practical applications is too early to say. Quantum computation, well, today we don't yet have a quantum computer. We have maybe a 10-qubit quantum computer. And the overhead to make quantum computation into a device-independent quantum computation is very large. So there's no knowing whether this will ever be implemented. So this is sort of the perspective for applications. I'm pretty confident this will be used. The others, well, we'll see. And so to conclude, well, non-locality, quantum mechanics, and randomness, they're intimately tied. And this topic goes from general philosophical considerations to considerations in applied physics. Thank you.
Any questions?
So experimentally, if you're not working in the quantum domain, it can be extremely hard to distinguish between something that's truly random and something that's simply chaotic.
Yes?
And I think that the one thing that I've gotten from this talk right now is that when you're working in the quantum domain, the fact that you can certify that something is random because of the Bell inequality is really something that just is not within the realm of classical mechanics. To my knowledge, there's no way of having sort of a certification that you have a whole bunch of bits out. There's no test that I know of when we're dealing with experiments with limited bandwidth and everything else that you can say this is truly random, or it might just be chaotic. Whereas it seems that with quantum mechanics you do have this guarantee. Is that Makes sense to you?
Yeah, perfectly. I mean, if you have a device which is supposed to produce random numbers and then it produces a sequence, like the troll in the example, there's no way you can prove that the given sequence is random. I mean, it's basically you're confronted with the uncomputationability problem in Turing, the halting problem of Turing machines. You can't prove this. And if I just give you the output of the quantum experiment, I can't prove to you, just the lights which light up, I can't prove to you that this is random. But if I give you all the data, then you can prove that what you've got is random. So there's a real qualitative difference, which, as far as I know, doesn't exist anyplace else in cryptography, that you can prove that a system works correctly just by analyzing the statistics. And that's basically physics is always about making models and then trusting and then comparing the models to experiment. And here we almost don't do that. We just run the experiment, analyze the data, and get the conclusions.
Yes?
So you mentioned that these molecules in the defense mechanism in the human body, right? They are random.
Yeah.
How do you know they are random? It's a serious question because they may appear random, or maybe there's some mechanism that actually produces only a certain number of configurations.
Well, the process, as far as I understand it, is rather complicated. So this molecule, in fact, the way it has a fixed part, and then it has parts which change. But these parts don't change in a completely random manner. They're actually like templates, which you take different parts of the protein in this region are coded from some sets, so that they sets which work well, and then these sets are assembled, and then there's some flips of the code here which take place, and then this is what is used. So it's a very, in fact, guided process to try to produce molecules which will work, and not produce molecules which won't work. Now, as far as I understand, from the people doing experiments on this, it looks random. At least you see that a biological, a human produces plenty of these different proteins in different ways, and you take another human, he produces other ones. Okay, I don't know if anybody, probably it's probably something like thermal randomness, which in the end is responsible. I don't know what is the basic mechanism. It's maybe not so important in that case. I mean, it must be just random with respect to proteins, to bacteria and viruses.
So I have a question. How do I quantify randomness? Like, this is very random, this is less random, this is not random at all. So practically, like you build a device, how would you justify the performance?
So there are many different ways you can try to quantify randomness. In these cases, for these applications, the technical way you do it is you say, well, I want that, okay, I take the output, which is the sequence of lights produced, of red and green lights coming out, and I try to look, I say, well, these sequences, they have some probabilities, which I can get some understanding of these probabilities from the study of the process, and I look what is the largest probability. So what is the sequence which has the largest probability, the most probable sequence, and this is a sort of very strong measure of randomness. Is out of this long sequence, what is the most probable sequence the device could put out? And then once you have, you know this, then there are techniques to compress this sequence into a smaller sequence which looks basically completely random. So if you have this guarantee that the most probable sequence, maybe suppose you've got 1 billion sequences and the most probable one comes out with probability 1 in 10 million. So it's 100 times more probable than if they're uniform. Then you could compress to basically 10 million sequences which are uniform, which all have equal probability. There are a lot of technical details, but this is the way, at least in this context, it's quantified and used.
Yes, please.
So in this randomness extension scheme you mentioned, you said you use some initial randomness to trigger the
Yeah.
process. So does this initial randomness need to be certified? And if so, do you think this is some kind of a loophole inside the entire process it sounds like a bit paradox.
Yeah, so that's a very good question. So we need, in fact, we need some initial randomness to set these settings. And so you could say, well, maybe this initial randomness doesn't exist. And in fact, the whole system, is deterministic in the sense, how this would work would mean that when Alice puts her switch in an up position, in fact, this knowledge is shared by all the particles in the system. They all know beforehand Alice is going to put her switch in the up position, Bob is going to put his switch in the down position, and therefore the particles adjust how they're going to turn on their lights. So this is a possible explanation. It's a weird one because you need, and in fact, so it's a weird one because you need everything to know beforehand what is going to happen. There's no kind of free will, nothing you can do. Alice can't do anything in her laboratory which isn't known beforehand to Bob, possibly thousands of kilometers away. And so, well, this is, as I say, it's a not very natural explanation. And so sort of my reaction to that is it would be very interesting if this was in fact true, and if one could find an experimental way, find an experimental signature that it's true. That would be a revolution in physics and in all of our understanding of nature. However, it's really against the way we understand nature, and so most likely this is, I wouldn't bet on this. The conservative version is that you can choose the measurement settings in such a way that they're not correlated to the rest of the experiment.
How is the research status now and the prospect when you're comparing the randomness and the human brain functions?
I don't know. There are a lot of processes in the human brains which are probably random, like when neurons fire spikes and things like that, but maybe not. I don't know.
Can I have a question maybe? So you mentioned that out of the three possible applications of divide randomness, the randomness, the crypto, and the computing, you are the most optimistic about the randomness in 5-10 years. So what kind of application do you foresee in 5-10 years?
For the randomness expansion? Well, the first, say, the proof of principle experiments which really work correctly are being done now. And so these need to be brought to a stage where they're reliable. And we work, for months on end. And then, the first application, you can just make the data public. And if somebody wants to run a Monte Carlo simulation where he doesn't need too much randomness, he can use this randomness, and he's guaranteed it's going to be better than any pseudo-random number generator.
You my credit card?
Then for crypto, then you need the randomness to be secret. So then maybe NSA or other security agencies may implement this and use the randomness. And randomness, what is interesting is that if you've got two sources of randomness, you can combine them to get a source which is as random as both separately. So you can just add it as an extra security. The whole question will be how fast can you make these systems sufficiently fast to generate useful amounts of data, and can you make them sufficiently robust and at term sufficiently cheap that you can implement them more widely. But at least, why not use this once as it works? And the proof of principle experiments are there. Especially the optical ones go pretty fast.
Any other questions? Not, then I guess we should thank again.